So now that we understand a little bit about solubility, we can talk about precipitation reactions. A precipitation reaction is when you take two solutions and you mix them together and a solid forms. That solid is called a precipitate. And when you mix these, and we did this when we did that copper cycle experiment, we had some solids form. It kind of looks like snow sometimes, if snow is black or green or whatever color it is. But a lot of times the precipitate is white, it looks like snow. Snow is precipitation, right? So the precipitate is a solid that forms, and then generally it settles to the bottom. It might do that quickly, it might do that slowly. In this example, yeah, question?
So when they like refer to rain as precipitation, it's considered a solid technically?
No. When the meteorologist refers to rain as a precipitation, he's using the word precipitation in a different context. Precipitation basically means something that's falling. And so we call these precipitates because the solid falls to the bottom. I mentioned the rain to help you, make that connection that the precipitate is falling to the bottom of the beaker. So in this example here, we've got potassium iodide and potassium nitrate. And when we mix them, we get potassium nitrate, which is soluble. And we can predict that from that table of rules. Potassium compounds are going to be soluble. And then we have lead iodide. Iodide compounds are generally soluble, except if the cation is lead 2, and then they are insoluble. So we have these two solutions, and what happens is the lead ions and the iodide ions are very strongly attracted to each other, and they precipitate out. So I have some crazy analogies for things, and if you don't like them, I'm sorry, but I have this fantasy world called Mrs. K's Chemistry Land. And in Chemistry Land, I think of this solution with potassium and iodide as being the potassium, I pointed to the wrong one earlier, sorry. The potassium is the guy and the iodide is the girl, because I said that metals are masculine and nonmetals are feminine. So here we have a guy and a girl, and they're swimming around in here, and they're coming, and this beaker, or this flask, is the party. And also at the party, we have lead ions, the guys, and nitrate ions, the girls, and they're mingling around and mixing around. And everybody's cool, and they're just mingling and having a good time. What happens when these two different solutions mix together is lead didn't see iodide before. And he gets an eyeful of iodide, and he's like, oh my goodness. And there's this chemistry that occurs, and they stick together. They're not mingling at the party anymore. These are the people that you find on the couch on the back porch making out while everybody else is in watching the Super Bowl or something, right? They're precipitating, they're going off by themselves because the attraction between them is very strong. How do we predict which things will precipitate? We look at the solubility rules. Lithium, sodium, potassium, ammonium, they are just not really attracted to anybody. They just aren't. Okay? Hydroxide, sulfide, those ones that are mostly insoluble, they'll go to the back porch with almost anybody. But there's a couple of ions that they're like, nope, not with you. Anybody else, but not you. Okay? So let's look at this and see how we would predict what's going to happen to this. What we're going to do is we're going to look at the two original solutions and look at the ions that are present. We have potassium and we have iodine. We have lead and we have nitrate. Well, we can tell from solubility rules and also from the problem telling us that this is an aqueous solution that lead and iodide are soluble together. They do not form a precipitate. And did I say lead?
Yeah.
Yeah. Potassium and iodide don't form a precipitate. Lead and nitrate don't. They came to the party just mingling and having fun. What we're going to look at is what happens if they swap partners. What about lead and iodide? Is that going to be a strong attraction? Is that going to be insoluble? Yes, it is. What about potassium and nitrate? We look at the solubility rules and say, no, that's still soluble. So those guys are going to keep mingling at the party. These are ionic compounds. You can't have strong attractions between two cations. It's electrostatic. It doesn't happen. Okay, things like that can happen with people, but it can't happen with ions because you've got positive charge and positive charge. They're going to repel each other. So you can't put potassium and lead together and have a precipitate. You can't put iodide and nitrate together. There's only one possible switching. You have to have a cation and an anion. Does that make sense?
So they form precipitate?
They will form a precipitate if these two possible products, if one of them is insoluble. It's possible that they could both be insoluble, but usually it's only one. When you mix two solutions together, you do not always get a precipitate. It depends on what the compounds are. So if we mix potassium iodide and sodium chloride, what are the two possible new compounds? Here we have potassium ion and iodide ion. We have sodium ion and chloride ion. What can happen is that we swap partners. So our possible products would be potassium with chloride and sodium with iodide. And to identify if one of those is a precipitate, we look at the solubility rules. Potassium compounds are always soluble. This will be soluble. Sodium compounds are always soluble. This will also be soluble. They're just going to keep mingling together, and so we say there's no reaction. A physical change has occurred. They have mixed, but there's no chemical reaction. We haven't formed a new compound. Does that make sense? Okay, so some of you like lists of instructions. Here's your list. How to write equations for precipitation reactions. Start with the formulas for the two reactants. Below the equation, write the formulas of the products that could form from those reactants. Check the solubility rules to decide if any of those are insoluble. Try to do the rules from memory first, and then check yourself by looking at the list. Don't just always look at the list every time. If all the products are soluble, write no reaction. If one or both are insoluble, then you have to put the states, S for solid, AQ for aqueous, and then balance out the equation. So it's always fun when you get no reaction because then you're done and you don't have to do any more work. Let's do an example. Write an equation for the precipitation reaction that occurs, if any, when ammonium chloride and iron 3 nitrate are mixed. So we're going to practice our nomenclature here. We need formulas for these. So ammonium chloride. Ammonium is NH4 plus because we memorize it. Chloride is Cl minus. It's in the 7th row, 7th column. It has a -1 charge. So when we put those together, we get NH4Cl. Is that a soluble compound?
Yes.
Yes. Ammonium compounds are always soluble. So that has the state symbol AQ. And then the other compound is iron 3 nitrate. So the first ion is iron 3. The Roman numeral tells us the charge. And nitrate is NO3 minus because we memorized it. When we put those two together, we get Fe NO3 3. Is that compound soluble? Yes. In the second row of the table, nitrate compounds are soluble, no exceptions. So this is aqueous. Any questions yet? Now what we need to do is swap partners and see what we end up with. So I would really, really encourage you to write the ions with their charges down here and then write the equation up there. Because now we have this already done for us when we go to swap partners. So iron came with nitrate. We're going to see how iron and chloride get along. And ammonium came with chloride, but we're going to try him out with nitrate and see what happens. So I'm going to write those new partners over here. This is adding, and so if I put the iron and the chloride first or second, it doesn't matter. 2 plus 3 is 5, and 3 plus 2 is still 5. So the order doesn't matter, and Mastering Chemistry won't care about the order either. So, yes?
About the mastering chemistry thing, I've noticed that it gets really picky about the parentheses, specifically around like nitrate and stuff.
Yep, it does.
Are you allowed to can you change that? Because like for example, I did like say for the ammonium nitrate, I put parentheses around the NO3 just to keep it by itself, and it marked me wrong for it.
Right, because you do not need parentheses if there's only one of the polyatomic ion. So it is picky, it's very annoying to students, but unfortunately most of the time it's right.
Okay.
Yeah. If you think that it's being unfair to you, feel free to text me, send me a screenshot. I can look at it. Occasionally we've had some weird issues with superscript, subscript formatting stuff, and I'm definitely willing to look at it. But yeah, technically it's wrong to put parentheses around ammonium nitrate because you only have one. Yeah, it's a good question. So let's see, ammonium paired with nitrate. And then, I didn't leave myself much space, we've got iron, 3+, and chloride. Now, before you actually make those into compounds, ask yourself, are these compounds soluble? Ammonium with nitrate, is that soluble?
Yes.
Yes, all ammonium compounds are soluble. So that one's going to be soluble. How about iron and chloride?
Yes.
I can't remember.
You can't remember.
Exceptions.
Yeah, so we're like, well, I think that chlorides were mostly soluble, right? And then there were a couple of exceptions, but we're a little fuzzy on this because we just heard about this today. So let's go back to the list. So here's the chloride. The exceptions are silver, mercury, and lead. So iron is not one of the exceptions, so iron chloride is going to be soluble. So they're both soluble. Do we have a chemical reaction? Nope. So then we write no reaction.
And that's it? You don't have to
That's it. You don't have to balance it or anything because there's no reaction that occurs. And sometimes we get even lazier and write capital N, capital R for no reaction. So whenever I go down Reed Avenue and I see the speed sign, you know, and it's malfunctioning, it says NR for no reading, I think no reaction, just because that's what NR means to me. Any questions? Do you see what we're doing here? We're taking these two ionic compounds that we started with, we're separating them into ions. Remember that ionic compounds have two ions, one positive, one negative. You're not going to have 3 or 4. So we have 2 here and 2 there, and we're just going to swap partners. So we still have a positive with a negative and a positive with a negative. Then you look at the table in your mind first, and then check yourself. See if they're soluble or not. Okay, here's another example. Write an equation for the precipitation reaction that occurs, if any, when sodium hydroxide and copper 2 bromide are mixed. So we need formulas for our reactants. They're ionic, so we need the ions. Sodium and hydroxide. Sodium is Na+, hydroxide is OH- because you memorize it. So this will be NaOH. Is that soluble? Yes. Sodium. Lithium, sodium, potassium, and ammonium, always soluble. So this is aqueous. And our other compound is copper 2 bromide. Cu 2 plus, and bromide. So when we combine that, we're going to get CuBr2. And with that one, if we put parentheses around the bromine, mastering chemistry would have a hissy fit because it's a monatomic ion and we don't need them. Is this soluble? Well, what's our best guess? Best guess is yes. Bromide compounds are generally soluble. There's a couple of exceptions. The exceptions are silver, lead 2, and mercury 1. So this is not an exception, so this is soluble. Now what do we do? Swap partners. So we're going to take these two inside together and the two outside and rewrite them. So sodium and bromide and copper 2 and hydroxide. Before we go to the trouble of putting them together, let's check the solubility. So sodium bromide, is that soluble?
Yes.
Yeah. Lithium, sodium, potassium, ammonium, always soluble. So this one's going to be aqueous. What about copper hydroxide? Hydroxide is in the bottom where it says mostly insoluble with exceptions. If we look at the exceptions, copper 2 is not one of them. So this is an insoluble compound. So we do have to finish this out. So sodium bromide, +1 and -1. So we just need one of each. That's going to be aqueous. And Cu2OH -1, we're going to have 2 hydroxides for the 1 copper, and that's going to be a solid. Then what do we have to do? Balance the equation. So hydroxide is a polyatomic ion, but it stayed intact. We can balance it as a unit. How many hydroxides are on the right side? 2. And how many on the left? 1. So we need to put a 2 in front of sodium hydroxide. So we've got 2 hydroxides and 2 hydroxides. Sodium, now I made there to be 2 sodiums. How many sodiums are on the right side of the arrow? 1. So I need to put a 2 here. I've got the sodiums taken care of. Bromine, now I have 2 bromines here. How many bromines over there? 2. And let's check copper. 1 copper and 1 copper. There we go. Okay, any questions? I would really, really like to see you write this stuff out underneath. It's not part of the answer, but that would be showing your work, and it's really, really helpful. The stuff at the bottom here. That's not part of the answer, but it's useful. Until you get really good at it, which probably hasn't happened yet, until you get really good at it, I would write those down.